Now let's move on to the very important section, which is the measurement of length, right? So the idea behind this topic is we are trying to measure lengths which are very, very large, and there are special methods of doing that. And at the same time, we are also trying to measure lengths which are very, very small, and there are special methods to do that too. So we'll first start with large lengths. How do we measure large lengths? See, the key idea here is that of parallax. Okay, so first we will try to understand what does it mean by parallax. The example that we have taken here is actually very, very simple. So this is sun and this is earth. Okay, rotation in 6 months. So in 6 months the earth would move from one point to its diametrically opposite point. So those 6 months can be December and June, which are given here, and there is a star right here. Okay, this is the star whose distance we want to measure, right? So how far is this star from sun? That is the idea. That is what we are trying to measure. That is the thing. Now we also have number of other stars which are much further away, right? So this star is relatively near in comparison to these other stars, and they are so far away, okay, that when we view the other stars from this point and from this point, the apparent change in their position is negligible. Okay, so we'll understand what do we mean by apparent change in position, but the idea is that these stars, they form a constant background, as if there is a screen which has been placed right there at the wall, and I'm trying to view this, for example, any object. Okay, so there is a screen which has been placed on the wall in front of me. Think about it this way, and on that screen there are a number of objects. Maybe they are gradations, maybe they are lines on that screen. Now I view it this way. My rays from my eyes will go through this and intersect the wall at some line. Let's say it intersect at the yellow colored line. Then if I view it like this, then it will intersect at a different point. Okay, so that is the idea behind parallax, that when we view this star from these two different points, it changes its apparent position. Really the position is not changing, but it would appear to me that first this star was in line with, let's say, this red star, and the second time when I viewed it in December, this star was in line with, let's say, this star. So its apparent position changed, not the real position. Really it's at the same place, and this change in position is actually measured by this angle right here. Okay, and this angle we call it the parallax angle. Okay, so this is known as parallax angle. Okay, this is parallax angle, and this the distance between these 2 points between which we have measured the parallax angle, this is known as the base. Okay, very, very simple. The concept is very, very simple, and here is an illustration of this particular concept. So if you look at this movie, what is happening here is that there is this sun. Okay, there is this star, our sun right here, and this is the earth which is rotating. Okay, it's one, and between these 2 points, okay, it's rotating. So this is the earth which is rotating around the sun, and we are trying to view a star at 2 different locations. So first the star is here, and then the star would come here, and we are trying to view the star at 2 different locations, right? So first let's start with the nearer star, so star which is near. Okay, so the first star is right here. So we are trying to view this star from earth, and as the earth revolves around the sun, the apparent position of this star would change. So first the line of sight would pass through here, then it would pass through here, then it would pass through here. Okay, so apparent position of this star would change, and notice that how that is changing. That change in the apparent position is actually described here at the top. So you will see that this star, it would appear to move back and forth right here. So let's just start this movie, and this will give you an idea of parallax. Okay, very, very simple. Okay, so as the earth is moving, okay, so it's moving like this, the apparent position of this particular star against the backdrop of other stars actually moves. Okay, and this is what we are seeing in this parallax. Okay, now what has happened is that I have moved this star further away. Okay, so there are 2 different stars, you can think of it that way. So first my star was here, and now my star is here. Now you will notice that the angles involved in the parallax are much smaller. Now that is the key here. Okay, so as we move away, the parallax becomes less and less. Okay, so the parallax actually decreases. So the parallax angle would actually decrease. So that further star, this is the nearer star, look how much it is moving. The further star is only moving this much, a fraction. Okay, so the parallax angle would actually decrease. So if the star is at the infinity, then I would have no parallax, and that is the principle that we are using it. These stars which are forming my background are at infinity, and we are not seeing any parallax with them, and using that as basis, we can compute the parallax of the nearer star. Okay, so hope the concept of parallax is extremely clear. Now let's move on to the some of the observations, right? So based on what we have seen, the animation and everything that we have seen, let's just first understand the observation. See, the first thing is that as the distance increases, the parallax angle decreases, that we have already seen. So further the star is, the less the parallax, the less the apparent movement. Now the other thing that we are seeing is that the background stars will be very, very far. So their parallax is approximately equal to 0, and we can neglect them completely. We are just saying that it's a constant background. That is what we are saying. Now what we have seen is that as the distance increases, the distance increases, the distance increases, the parallax angle decreases. Therefore, the parallax of a star is inversely proportional to its distance from the sun. Now, that is a very, very important result right here. Okay, so if the star was 2 times away, it would produce half as much parallax angle. If the star is 2 times nearer, it would produce, if it comes near, then it will produce twice as large parallax. Okay, and this parallax is actually known as trigonometric parallax, because we will be using trigonometric methods to compute the distances. See, the idea is very, very simple. How do we compute the distance? We can actually look at it right here. See, so why are we doing all this, right? That is we'll get some idea here. See, this distance we know how far is the distance between Earth and the Sun. So Earth and the Sun distance we know, therefore this distance also we know. This is the base, we already know this distance. Okay, this angle we have really computed. So we know how much this angle is. Okay, so this is P, so this entire angle will be 2P, and this is something that we have measured. We are using our devices, the telescopes and everything, to measure this angle. Once we have measured this angle and we know the base, then we can compute this distance D right here, the distance between the sun and the star, and that is the idea of using this method. So we are using this trigonometric method to compute D with the help of this parallax angle and the distance between the Earth and the Sun. Okay, so that is the idea. Now let's move on. Okay, so basic idea we have now understood. Why we are doing this, I mean, that is something that we should have explained early on, but that is fine. So now let's move on to the next thing, why it is very, very important, and it comes in the concept. In this concept, it's very, very related, and that is the concept of a radian. And we will visit and revisit this concept of the radian until you are tired. This is very, very important. See, radian is the measure of an angle subtended by an arc, and the measure has been created in such a way that if the arc length, the length of this arc is equal to the radius, then the measure of the angle subtended by the arc will be equal to 1 radian. Okay, so that has been designed in such a way. It has been designed in such a way. Okay, so that is the definition of a radian. Okay, now let us just do the parallax calculations. What does it mean by calculating the parallax? See, that is what we have done. So these are the 2 positions. Okay, this could be sun right here. Okay, and this could be our 2 positions, diametrically opposite positions of the Earth, or this could be 2 positions on the Earth itself. So on the Earth itself, we have one location somewhere in Australia, we have one location somewhere here in India, and there are 2 locations, and we know the distance between those 2 locations. So this B we know. Now this angle theta we know. Okay, one of the things, the definition, when we define the radian, one of the things that we forgot to note here is that the radian measure of an angle, right? So if I have this theta right here, it's an angle which we have expressed in radian, is always equal to arc length. It is the ratio of arc length by radius. Very, very important result. Okay, and that is true. See, if this radius, it has been defined in such a way, if this length of this arc is r, the radius here is also equal to r, then what would be the ratio? The ratio will be r, arc length by radius, and that will actually be equal to 1. And we know that this angle is 1 radian. So radian has been defined in such a way that the measure of an arc at the center, the angle subtended by the arc at the center, when it is defined in terms of radian, will always be equal to length of the arc divided by the radius. Now we use that result right here. Okay, so we know that this theta will be equal to, now one assumption, one small assumption that we are making is that this d is so much larger than b, that this d is so much large, it is very, very large than b, that we can ignore that there is an arc here. We can just assume that this b is actually arc length, and that kind of makes sense, right? If you think about it, then what would happen is that if this b becomes very, very small, right? If let's say that this entire, instead of this entire thing being b, if this was the only b that I had, okay, this theta was so very small that the b was like this only this much, then the arc length would be somewhere here. Okay, this would be the arc length, and you would say that, oh sir, this line and this arc are so close together, then I can just assume that if this distance is b, the arc length would also be b. There is so little difference between them. That is one assumption that we are making here, and that assumption is very, very important, that d is much larger than b, and that allows me to take this b as arc length. Sorry, I forget to write t every time. Okay, so now that we know, so this theta we know is length of the arc, which we have assumed would be equal to b, okay, roughly equal to b, and divided by the radius, which we equal to d. Okay, so that is the basis. Okay, but remember, this theta is in what? It is in radians. So then I can use this to actually compute the value of b I know. So I want to compute the value of d, the distance of the thing that I am measuring. Okay, that how far it is, how far it is from, let's say, earth, or how far it is from sun. This d I really want to measure, and this would come out to be b by theta. Very, very simple result. Okay, so that is the idea behind this parallax calculations. Now let's solve some examples, and that would make this thing even clearer. Now, one of the things which has been discussed in your, not discussed in your book, but we have problems based on this concept, is the concept of a parsec. Okay, so this concept of a parsec is a unit of length. So that is the first thing we need to understand. What is parsec? Parsec is the unit of length. And what is the basis for this measurement? Okay, so parsec has been defined as, if this angle, this parallax angle, okay, so parallax, the angle here and here would be same. If this parallax angle is equal to 1 arc second. Now what is 1 arc second? So 1 degree, okay, if I divide it into 60 minutes, then I have 1 arc minute. Now this 1 minute, if I divide it into again 60 seconds, okay, then I have 1 arc second, and that 1 arc second, so it's 1 degree divided by 60 into 60 of then this is equal to 1 arc second. Okay, so it is 1 by 3600 of a degree. Okay, that is the 1 arc second. Okay, and again we are using the same unit that we use in the case of a clock, right? So in the clock, what happens? 1 hour is equal to 60 minutes, 1 minute is equal to 60 seconds. Similarly, we have defined it that in 1 degree we will have 60 minutes. Okay, and we write it as, okay, so 1 of this, okay, so 1 by 60th of a degree, we write it as 1 minute. Okay, and there is a 1 dash right here, and similarly 1 by 60th of this 1 minute, we write it as 1 second, and this is given as 1 double dash. Okay, so there's a double dash right there, double ticks if you will. Okay, so that is the idea. Okay, so that is the 1 arc second. So if this p is very very small, it is 1 by 3600th of a degree. Okay, that is how small angles we are talking about. If this p is 1 arc second, then this distance between this star and our sun would be 1 parsec. So that is the definition of 1 parsec. Okay, and how have we calculated this parallax? We have calculated this parallax from the center of our solar system, which is the sun, to the earth. So that is the parallax, that is the angle. Okay, it is not this angle, it is not the angle calculated between the two positions of earth. Okay, that would be 2p, that would be 2 arc second. Okay, so if I were to extend this line right here, okay, so then this actually would be equal to 2p, okay, or 2 arc second. But that is not what we are saying. We are saying that from the sun to the earth, one location of the earth, if the angle, parallax angle, is 1 arc second, then the distance of that star whose parallax angle is 1 arc second is equal to 1 parsec, and that is the definition of the parsec. Another thing to note here is that this distance between the earth and the sun is known as 1 AU, or 1 astronomical unit, and this distance is approximately equal to 3 into 10 raised to power 11 meters. So that is another thing that we are looking at, that this distance is equal to 3 into 10 raised to power 11 meters, or 1 astronomical unit between the earth and the sun, and that is the standard distance in our solar system, and that is why we have defined the parsec to be in that terms. Now this is 1 parsec. If the star is nearer, let's say that is parallax angle is larger, then let's say if it is near, the parallax angle instead of being p would be 2p, and its distance would actually be equal to half parsec. Okay, so that is why we have used this unit. We have created this convenient unit, and we can easily, just by looking at the parallax angle and comparing it with this star, this particular star which subtends an angle of p, just by comparing it with this star, we can come up with the distances of other stars, relative distances of other stars. Okay, in terms of parsec, things become very very simple. Now let's just compute the value of 1 parsec. What does it really mean? Okay, and this is a problem given in your book, and it is very very kind of illustrative. Okay, it is it is kind of important also. Now this angle we know is equal to 1 arc second, and we'll just use this convention, 1 arc second, and this distance is actually equal to 1.5 into 10 raised to power 11. Okay, sorry, so I made a mistake here. We'll just correct it right now. This distance is not equal to, this distance between two positions of the earth is 3 into 10 raised to power 11, but this distance 1 AU is equal to 1.5 into 10 raised to power 11. Okay, so note that correction. Now let's move on. Okay, so when earth is this diameter of the earth's orbit is actually equal to 3 into 10 raised to power 11. The distance between the sun and the earth is approximately equal to 1.5 into 10 raised to power 11. Of course, that changes all through the year, but we'll not go into that. We'll just assume it to be this way. And this we know is 1 parsec. So our objective is to compute the value of 1 parsec in terms of this meters. That is our objective. Now we already know that this 1 degree, we already know that formula, that theta, this 1 degree is equal to arc length, which is b. Okay, so we'll just call it for reference, we'll just call it b by 2, because earlier we were saying b. Okay, so this is b by 2, this entire thing is b, so this is b by 2. This entire thing is, we will call it b. Okay, and okay, so this is half. Okay, this is half, so half will take it to be b by 2 divided by this distance, which is 1 parsec. Okay, so 1 parsec, we don't really know what its value is, so we'll just call it capital D. Okay, but this theta we know, and what is that theta? This theta is equal to 1 arc second, and 1 arc second is actually how many degrees? We know that is equal to 3600 degrees. Very very simple. And of course we also know that this many degrees. Now can we convert it into radians? Okay, because this theta we need in radians. Okay, remember that this angle has to be in radians for this formula to really work. But here we have been given our angle in terms of arc second, so we have to convert it into radians. Okay, so 1 degree we have converted we have converted the 1 arc second into degrees. So this is degree. Now we know from our maths that what do we know? We know that 360 degrees is equal to 2 pi radians. So 1 degree is equal to pi by 180 radians, and therefore if I multiply this entire thing by pi by 180, I will get the number of radians. So this is the angle in radians. So we have been successful in measuring the angle in radians. Now this angle in radians, if you compute it, this comes out to be pi by, so you can do this multiplication, and this comes out to be 648,000. Okay, and you don't have to be so accurate. Even if you were to use 650 instead of 48, you can use 50 also, and that would have also given you kind of the correct answer. It doesn't have to be so accurate. And this we know, okay, this is the angle in radians now. So we are talking about radians now. So now we can actually equate. So b by 2 is how much? 1.5 into 10 raised to power 11, and divided by, we want to know what the value of this is. So this remains d. Okay, so we know it is 1 parsec. But how much 1 parsec? What does it mean when we try to convert it into 1 meter? And this becomes, d will come here. So this becomes 1.5 into 10 raised to power 11 into 648,000 divided by pi. Okay, so we are dividing this entire quantity by pi. Okay, and if you compute this value, then this distance d would roughly come out to be approximately, okay, it will come out to be 3.1 into 10 raised to power 16 meter. And this distance we also know it is the definition of 1 parsec. So now we know what is 1 parsec.